This problem comes from Katrina Shearer, a math teacher from Cambridge, England, who was gracious enough to allow me to use a few of her problems in these videos. If you enjoy the problem and happen to be active on Twitter, you can follow her here, and I'd be remiss if I didn't point out that she also has a book for sale containing a bunch of these fun little geometry problems. One of the things I really like about her problems is they're fairly self-explanatory, but just to be clear, what's pictured here are 5 different squares, and in the case where there's a number given in the middle of the square, that represents the square's area. The goal here is to figure out the area of the blue square, the toppled square, as Katrina named it. The 3 red squares on the right are tangent to the blue toppled square, the uppermost sharing a vertex with that square. The brown horizontal line serves as the base of 2 of the red squares and intersects a vertex of the blue square. The fact that all of these objects are squares allows us to go back and forth between the area and the length of one of their sides pretty easily, so it's probably worth the time to calculate the side length of the 3 red squares whose area is given. Note that the square root of 27 is the same as the square root of 9 times the square root of 3, and the square root of 9 is just 3, so the square root of 27 is just 3 root 3. Similarly, the square root of 12 is the square root of 4 times the square root of 3, and since the square root of 4 is just 2, the square root of 12 is 2 root 3. There's not really any simplification that we can do for the side length of the smallest square, so we'll just note that it's the square root of 3. Where do we go from here? Well,
look for a pair of similar triangles.
so before I go using that advice, I want to make the point that there's lots of different ways to solve this problem. I'm just going to demonstrate a couple that were the most natural to me. If I'm going to use similar triangles, the idea is if we could figure out the side length of the blue square, we'd essentially be done. So maybe one of the triangles that I should look at should be a triangle involving this side. Using the known heights of the 3 red squares, I could figure out the height of this right triangle is just 6 root 3. Now all we need is a triangle that's similar to that purple triangle, for which we know the length of 2 of the 3 sides. Well, what about this triangle? The length of a side of the middle square gives its height, and the difference between the length of the side of the bottom square and the length of the side of the middle square gives its base. These triangles are similar because they have 3 pair of congruent angles. I think the fact that they're both right triangles is fairly obvious. The bottom left angles are congruent because they're what are called corresponding angles of the parallel lines formed by the top and bottom of the square with area 27. And once we know we have 2 pair of congruent angles, the fact that the interior angles in any triangle have to sum to 180 degrees guarantees a 3rd pair of congruent angles, which gives us 2 similar triangles. The way I think about similar triangles is one is just a scaled up version of the other one. So by comparing the 2 heights, we see that the purple triangle has edges whose lengths are 3 times as long as the green triangle. So the base of the purple triangle must be 3 times as long as the base of the green triangle, so the base of the purple triangle is 3 root 3. And now that we know the length of the legs of the purple right triangle, we can use the Pythagorean theorem to relate together the sum of the squares of those lengths with the square of the length of the hypotenuse. Informally, a squared plus b squared equals c squared. With the help of a little bit of arithmetic, we can figure out that the square of the hypotenuse is 135. At this point, it's tempting to take the square root to solve for the length of the hypotenuse, but don't bother. Remember, our goal is to figure out the area of the blue square, and the area of the blue square is the square of the length of a side of that blue square. But the length of a side of the blue square is exactly the hypotenuse of that purple triangle. So the hypotenuse squared is the square of the length of a side of the blue square, which is the area of the blue square, which is the answer we were looking for. We're done. The area of the blue square is 135. Even though we have the answer, I'm not quite ready to end this video. I still have 2 more things I want to show you. One is I want to show you how you can come up with that answer, 135, without ever figuring out the length of the hypotenuse, which is kind of surprising. And then I also want to leave you with a challenge question. So first, an alternate method of solution. To me anyway, the most obvious way to figure out the area of the square is to figure out the length of the side of the square. And since the length of the side of the square is the hypotenuse of the triangle, it seems like that's a length we need to know. But look at this picture. Can you see where this is going? If we start with the area of the outer square, maybe I'll make it green to differentiate it, and subtract out the 4 purple triangles, we'll be left with exactly what we're looking for, the area of the blue square. To figure out the area of the green square, all we need is the length of one side of the green square. But the side of the green square is just made up of the 2 legs of the purple triangle. So the area of the green square is just the square of that sum. 3 root 3 plus 6 root 3 is just 9 root 3, and 9 root 3 squared is just 81 times 3, or 243. To figure out the area of the 4 triangles, we'll just use our half the base times the height formula, noting that since we have a right triangle, the base and the height are just the length of the legs. It's easy enough to calculate the area of these 4 triangles to be 108, and when we subtract that area from the area of the green square, we're left with the area of the blue square, which we see again is 135. Same answer we got before, but this time without ever calculating the length of a side of the blue square. There are no doubt other ways this could be solved, but maybe I'll leave that for the comment section, and end this as I always do with a challenge question. In the original diagram, there was a square in the bottom left that was only used to support the toppled square. And while it wasn't stated that it did, the left edge of that square appeared to line up with the leftmost vertex of the toppled square. If in fact that was the case, then what would the area of that red square be? As always, I'd love to hear thoughts, comments, questions, solutions in the comments.